So I would say we can continue. It's 3:45. So we would like to briefly look at Biolig. What's this? Now it works. Biolig process, that's a process that has been developed here at KIT for transforming biomass into high quality fluids. So here there are two parts in this system. There is the part that can be done in a decentralized way. So at small villages, for example, they can take the straw from the field, transform that into a finer material, and then it is heated up very much. It's not burnt, but it's heated up in a very hot sand, and this then is transformed into what is called Biolig syncrude, some kind of like tear ähnlich. I don't know what tear really is. Like it's Biolig syncrude. That's the name, and so it's heavily condensed, and this condensed material then can be transported to some factory where it is processed in a process chain. Like there's gas generated from that. So this is some process where gas is produced from the Biolig syncrude, and then this is refined and reconditioned in some way, and in the end, like after they have this synthesized gas, this is transformed through several stages into high-level gas for not gaseous form, but liquid, which is having something like 100 octane, so a really high quality fuel for vehicles, for example. And this is running. It's operating in, like, there's the plant, the Biolig plant here in northern, the campus north. You can visit that, can see it is industrialized or industrial size factory producing now liquid from biomaterial, and so there's an example of that. Like this Biolig syncrude, and the energy density is going from like 1.5 gigajoule per cubic meter straw up to 20 gigajoule per cubic meter syncrude, and then up to 36 gigajoule in petrol, diesel, or kerosene. And so this is like this image here, having a gas station or a fuel station on a straw field. Yeah, it's not working directly there, but you need a little bit of industrialized processes, and this is developed here at KIT. So it's running. So in 2014, it was the first time the whole process ran through, and now it's really working. Okay. Now, what about the interplay between renewables and conventional power? I entered this slide here. If you have printed it out before, it was not in there. I added this slide because I wanted to add this remark here. If we look at the way we actually combine power generation from renewable sources and from conventional sources, we have to satisfy the load that is there, the demand for energy. And for the demand, you have a certain annual load curve, and so that is the load from the year 2014, given here in black. So it's a difference of about 43 gigawatt from the lowest level to the highest level of demand. And then you have a certain power generation from renewables, and that gives the residual curve for how much energy or how much power has to be generated from other sources than renewables, for example from conventional power plants. That's the curve, the blue curve here, the residual load that has to be covered by conventional power plants. And this is still quite a bit. It is like a larger difference between 62 or difference of 62 gigawatt from peak times to very low times. And now if you look at the same curve predicted for the year 2050, when we have mainly like 85% or 80 to 85% power generation from renewables, the curve will look like this. What does this mean? We will have, as I mentioned already a few times today, quite a surplus of energy from renewables, from photovoltaic and from wind. You see here that's at minus 140 or something. So it's a surplus of power generation, a difference of about 200 gigawatt between the peak demand there and here that's surplus. No power generation from conventional power plants is necessary, but there is still this area here. So what we have is that in the future there is a high surplus of energy, but not always at the appropriate time. And not always is exactly this area, which is a demand for power from other sources than renewables, because there is not sufficient power generation from renewables. And it means even in the year 2050, from this forecast here, we will still have quite some demand for power from conventional or from other sources than photovoltaic and wind. And the challenge would be how to make it possible that we can satisfy that demand with power that is there in abundance at other times. Then we have in some way either move the demand, the load, to the times where we have high oversupply of power, or move the oversupply of power to the times where there is this demand that is not covered so far. That means, like, to move the power over there means to need or to use some storage facilities, which is not storage just for a few hours, but maybe for a longer time. And this is one of the major challenges. So what we need is this load or also generation flexibility. And so this diagram shows the interplay between renewables and conventional power generation. Even if we have quite a surplus, even more surplus than today, of power generation, there are times where we need the other power generators, conventional power plants, and this has to be avoided. That's what we have to work on, to make sure that we get sufficient flexibility in demand for power and in, well, some way moving the power surplus to other times. So flexibility is the major challenge. Now people could say, well, just reduce the demand and then the problem is gone. This does not work. Certainly it may be that if we reduce the demand, this curve here will go down. But it does not change, like even if we have a very efficient, much more efficient way of using energy, we will still have the times where there's no sun and no wind. And those are the times where we have this extra demand for power. And so this flexibility has to be there in some way. This is the major challenge. Efficiency, energy efficiency, is a nice thing. At times where we will have an abundance of power, people will not talk about energy efficiency anymore. Yeah, but they will all talk about flexibility. That's the major challenge. Cannot emphasize that enough. Okay, and the fact is that if you look at typical programs, funding programs, research programs, they mainly talk about energy efficiency. And this is not our problem. The problem is energy flexibility. But flexibility is something which will involve many people. Yeah, they have to modify their habits. in order to be able to move the demand. And so this is not that easily done. Okay. Now we know how to generate power. How do we transmit that? How do we distribute that? So the traditional way is to use this power grid where we have 4 different network layers. We have transmission distribution networks. We have the transmission layer where power is transmitted over larger distances in the ultra-high voltage network. 380 kilovolt, 220 kilovolt, different standards are there. And then there are the high voltage network, medium voltage network, and low voltage network. Different voltage layers. We use them. I have that actually on one of the next slides. So the reason for different voltage levels is that we want to reduce the loss of energy. So if you have a cable and you want to transmit power over such a cable, there's a certain resistance on that cable, and the higher the current is, the higher is the energy that is lost. You have heat development, so energy is lost by being transformed into heat. The cable is heating up due to the resistance of the cable, and the higher the current is, the higher is this effect of heating up. Now if this depends so much on current, since energy is, or power is the product of voltage and current, if you increase the voltage, you decrease the current, and so having higher voltage, you have less current, you have less heating up effect, and so you can transport the energy and reduce the loss. That's why we have the high voltage layers, because there we reduce the losses due to heating up of the cables. Okay, so that's why we have these four layers, and we also have a European network of all the power grids. So we have one large connected network. This is different, for example, from North America. There it is not just one network. There it's a collection of different networks having different frequencies and things like that. So they are not operating it as one large network. But in Europe we have one large network. In Eastern Europe it is a little bit different, but it's mainly one network. It's the European Network of Transmission System Operators for Electricity, and the acronym is ENTSO-E. That's the European system. And so that's the different layers, and this ENTSO-E is like this. I copied that from the description of ENTSO-E. It is committed to develop the most suitable responses to the challenge of a changing power system while maintaining security of supply. Innovation, a market-based approach, customer focus, stakeholder focus, security of supply, flexibility, and regional cooperation are key to ENTSO-E's agenda. And here on the next paragraph there are all kinds of topics that they address, and I have linked it all to the appropriate websites, and so you can just look it up and look at the different topics like drafting of network codes and contributing to the implementation, regional cooperation through the regional security coordination initiatives, technical cooperation, publication of summer and winter outlook reports for electricity generation, development of long-term pan-European network plans, coordination of research and development plans. So doing many things together. Just yesterday I was at a conference where some TSO like from Austria said that they are closely cooperating now, like different from former times. They're closely cooperating with Germany and France and a few other countries on the markets, on the balancing markets and intraday markets and so on. And they could save significantly, like just for Austria, they saved in the range of 20 to 50 million euros just because they cooperated and agreed on how much balancing power actually was necessary to be bought on the markets compared to evening out balancing in between the different networks. So cooperation there is something which is really a benefit also for, like first for the transmission system operators, but certainly also for the customer because the costs go down. A lot of things they do together, it's good that they do that, and so the transmission system operators, like this network of transmission system operators, they are responsible for the stability of the infrastructure. That they can always transmit the power that is fed in and needed by those who demand it, who consume it. So one view again on this drawing of the system as it looked like in former times, where we have the different layers again with the central power plants, and we have here the value chain, and this is being changed now. Some of these centralized plants are replaced with offshore wind plants. I said that is something which is a favorite type of replacement, because then the grid structure need not change. But we have also onshore wind power plants, and they are attached to high voltage or medium voltage layers, and we have some large-scale solar farms. They are attached to the medium voltage layer, and we have quite a few on the rooftops, and those are attached to the low voltage level. And this low voltage level was never designed for being a place where power is fed into the system. This is just completely against the original design. And we certainly have here these houses which now play an active role, and we have all kinds of electric vehicles which are extra consumers. And if you look at the amount of power a vehicle needs, driving something like 15,000 kilometers per year, you have a power consumption of around 3,000 kilowatt hours, and that means that's about the power consumption of a two-person household. Yeah, so if we have as many vehicles as households, you have as much power consumption as you had for those households. And so this is additional power consumption, but it's also power storage. And so the storage facilities could be used in a reasonable way. We will see how that actually is done in some later parts of this course. Okay. Again, back to the power transmission network. We have the centralized power generators, we have the high voltage distribution or the high voltage transmission network, and then we go to the low voltage grid and all the end consumers here who actually then get access to the power. So usually this is completely unidirectional energy flow, tree structured but reconfigurable. If we go back to the previous slide, I said tree structured. Now if you look at this structure here, this is not tree structured. There you have a radial network in a rural area. This is more or less tree structured. Here you have interconnected network, an urban meshed network. So urban network structures are meshed networks, which can have cut points at different places, and but it's a flexible type of network, which is like here at Karlsruhe, it's quite stable and has quite some capacity. They are not afraid of additional demand by electric vehicles, although I don't know whether they have looked at it appropriately so far. Now, essentially, it is tree structured, but it's not necessarily having such a radial structure as you can see here, but those ends here may sometimes be connected, although for electrical reasons it has to be cut at some place. But if you have such a ring structure, you are flexible in at what point you actually cut it into two parts, and so this provides also some kind of flexibility. But this is beyond the things that we are addressing in this course. Why do we have the different layers? I mentioned that already. Minimize the transmission loss. we want to, like as I said, power transmission depends on voltage and current. For fixed voltage, amount of or a fixed voltage, the amount of energy transmission depends on the current. So if we put up the voltage, then current goes down, and so if we have too much current, then the power lines get too warm, and we want to prevent that. And so the longer the distance is, the higher the voltage, and the more power is needed at a certain point in the network, the higher voltage level has to be directly connected. For example, the KRT campus is directly connected to the medium voltage level. Also, our Energy Smart Home Lab is directly connected to the medium voltage level. Certainly not directly, but almost directly. It's certainly transformed down to 0.4 kilowatt. Okay, so that's why we have these different layers. And then nowadays people talk quite a bit about alternating current versus directed current. Like usually in the power grid, everything is transmitted with alternating current, but transmission loss is lower if we have directed current, because this continuous switching between like these alternating currents is also leading to a heating effect in the system, so it's extra losses. And if we have DC power transmission, it's reducing the loss. And so people talk very much about ultra high voltage directed current power lines when they talked about Desertec. Now they're also talking about connecting the offshore wind power plants to the areas in southern Germany where power is needed. So that's this valid point here, that for transport of power from large offshore wind power plants to mid and south Germany, high voltage DC lines are being planned. They are there to some extent already. They need to build new components for that because it's a different technology. You have to be able to then transform the DC into AC again, and this is quite some technological challenge to build it at the dimensions that are needed there. There are also suggestions to reduce power loss just by using reduced frequency. So for example, the train system has its own power supply system at 1/3 of the frequency, so not 50 hertz, but 16 point something, almost 17, just 16.8 or something hertz. And if you reduce the frequency, then you also reduce the loss that you have. So this would be some kind of alternative, but like there are different suggestions by different power engineers, and the current plans are to go for DC lines. There are also some thoughts about, well, if you look at the devices that we are using, our laptops, our computers, LED lights, like the lighting in buildings, computing power, quite a few devices in a household only need DC power. They don't need AC power. We have all our connectors that transform the AC power into DC such that our devices can use DC. If we would have a DC infrastructure in our houses, then that might be more reasonable, might be cheaper. So people think about what reasonable infrastructures could be that are based on DC. It's an old discussion. When the first networks had been built up or had been constructed, the first engineers at that, or the power engineers at those early times, they discussed heavily whether AC or DC would be the choice. And for some reasons they decided for AC, has certain advantages. That's something for the power engineers, it's not my topic, but it's interesting to see that now these discussions come back again because of all the changes that we have in the systems. Also the power that we get from PV cells is DC power. Then we have the inverters to make it into AC, and then if you want to store it in a battery, you have to transform it to DC again. If you want to get power from a battery, that's DC. If you want to use it in your house, you have to invert it into AC again. And every transformation is a source of energy losses. So the efficiency is going down because of all these inverters, and it would be much more reasonable to have just one type of power transmission. So DC might be an alternative, to have almost only DC. Yeah, so these are all the kinds of things that people talk about. If we look at Germany, we have, wanted to draw something here. There is the grid in Germany, and there they are, as you know, they wanted to build these new power lines, DC power lines, to connect southern Germany, southwest Germany. You know that it's supposed to go around Bavaria because they don't like high power lines. They certainly say we have to get power, but not this NIMBY, or you could say not in my Bavaria. Yeah, so should go to Hessen and Baden-Württemberg, and then direct connection into Bavaria, but it should not cross Bavaria and lead to other countries. Similar to the storage facilities for nuclear waste, certainly are never meant to be in Bavaria. They have the largest number of nuclear power plants, but they always objected to attempts to explore sites in Bavaria for storing the energy. It should be in northern Germany somewhere. Now this is Bavarian attitude. So, okay. Now I mentioned the European network. This is an old drawing. This is an old graphics, just showing that energy is flowing back and forth over the different borders between Germany and Poland, Netherlands, Denmark, and so on. A lot of power is moved down to Italy, and then some is going to Switzerland, to Austria, and it's going back and forth, both sides, both ways. Just showing that there's quite some exchange of power between the different national grids. As said, there is this European network of transmission system operators, and they operate, or they take care of the stability of the European network. And that means that power has to be moved back and forth between the different networks. So that's the ENTSO-E network, and it controls the cross-border exchange of electricity, where actually Poland is trying to cut that and enforce barriers that they don't have to take the power from Germany, because they don't want to suffer from our surplus. They have their own power generation from coal, and they're happy with that, and don't want to have the surplus wind power from Germany. Like a lot of wind power is generated in this area here in East Germany, and so they don't want to have that. It has to be moved down there. Okay, it's an old diagram just to indicate that there is an exchange. There will be other diagrams available. This link here does not work anymore, so this is no longer valid. And I took it from that link at some time, but this link does not work anymore. Okay, so it is not the situation that we have in 2014 or 2016, I should say. And but you can look up, like there are statistics about the import and export of energy between the different countries. Now, when we talk about the shifting of energy, movement of energy between different areas of the grid, the reason is that we must have the steady balance of demand and supply. And in some places we have more demand, in some places we have more supply. And so we must make sure that this is taken care of appropriately. And as I said already, the traditional assumptions of energy management and control are that demand cannot be controlled and electricity cannot be stored. And so we always need an immediate balance between demand and supply in the power grid. So you have to make sure that there's exactly the needed supply of electric power, having the demanded quality with respect to voltage and frequency. For like frequency, certainly only for AC transmission. For DC, there is no frequency. And so for AC transmission, so this is one of the advantages of the AC system. We have frequency as an indicator of surplus or deficit or an unbalance in the system. If the frequency is going up, we have too much supply. If the frequency is going down, we have too much demand, deficit in supply. And so if you don't have frequency, it's much harder to actually provide stability for such a system. So for AC transmission, these imbalances lead to changes in frequency, and that's the key to actually stabilizing the system. And we need a structure for power management and control, and this is, for that, the network is structured into physical and logical zones and groups. And this is indicated in this slide here. We have the logical structure of the power grid. We have the power transmission network, as you saw on the slide from Germany or from Europe. And you have balancing zones. And for every balancing zone, you have a transmission system operator, which is responsible for making sure that within that balancing zone, everything is balanced. If it does not work, they have to exchange power between neighboring balancing zones. And maybe, like the national power transmission networks, they are exchanging power between the different power networks, or you could say it's just a balancing zone of a neighboring country. And within a balancing zone, we have balancing groups. And balancing groups can be just physical groups of end consumers, or also providers of energy, or it can be a virtual arrangement, a virtual collection of end consumers. But it is some group of endpoints of the energy system in the distribution, like those endpoints in the distribution network, and there we have a balancing group manager who is responsible for the balance of supply and demand in his balancing group. So the balancing group manager actually makes a forecast of the energy needs for the next day. The day ahead demand is calculated by the balancing group manager. The balancing zones managers, the transmission system operators, they collect all the forecasts from the balancing groups. And then you must make sure that you have sufficient power for the next day. That's the day ahead market. Then during the day you might have changes, and some of those changes can be dealt with on the intraday market. And if it's too short time frame, then you need balancing energy in a different way. But there are some market structures, and then there is the balancing energy, which we will look at in a moment. So these are the German balancing zones. 4 balancing zones have developed from some traditional structures. You see, obviously, this is here just the old division into East and West Germany. And then in West Germany, we have also some traditional separations of the balancing zones. And there are, like we have the unbundling. It used to be just balancing zones of EnBW, E.ON, RWE, and Vattenfall. Unbundling meant that they had to be separated. The operation of the networks had to be unbundled or separated from providing energy. And so we have Transnet BV, we have Tenet, Amprion, and 50 Hertz. and we have more than 900 balancing groups in Germany. And so we have these four balancing zones and more than 900 balancing groups. In other countries, the situation is very different. For example, in Great Britain, there's one balancing zone. And so it's a completely different system. In France, it's also different. And regulation, as I said, calls for strict separation of smart grid and smart market. The transmission system operators must not buy or sell energy on the day-ahead market. This is something which is done by the balancing group managers and their they have to, or the utility companies, they buy the energy and sell the energy, and the smart grid operators, transmission system operators, distribution system operators just must make sure that the energy can be transmitted and distributed safely through the network, so that the network is stable enough to actually transport that energy. But they are not allowed to deal on the market, to trade energy on the market, except for the power that is coming from photovoltaic and wind. This actually, to quite some extent, is sold by the transmission system operators because they are obliged to just take that and then they are offering that again on the market. That's the only exception. Okay, now we have the balancing zones and load balancing. And we want to have a load balancing, we want to have a stable frequency of 50 Hertz. So let's briefly look at the current frequency. I did not start this here. I have to, what is this? Okay, then I go on to that. There's no wicket here, so very strange, and no Eduroam. Let's try that again. I connect it to the mobile system. Let's wait a moment. There it is. And then we should be able to see the, it's an English course, so it should use the English version. So that's the mains frequency. And here you see the current frequency that we have, 50 Hertz. It should adjust to the current frequency. Certainly the current frequency, yeah, you see, now it's going down. Now it's the measurement. It's not exactly 50 Hertz in the moment. It's 49.97. And you see that we have a quite low frequency. And you see that we have 395 megawatt of primary control that is used to stabilize the frequency. Yeah, this is online indication here. This is a proportional use of primary balancing energy, primary control energy. And so in the moment, if the frequency is going down, we don't have sufficient generation of electricity, and so something has to be used. There is additional, there are 142 extra megawatt which are used to get the frequency up again. You see it works, it goes up slightly, and these are the regions where this region here between 50 and 50.02 is not really a dangerous area, but if it goes beyond that, then they have to do a little bit more, and it must not go below 49.8 or above 50.2. If it's going outside those bounds, the system collapses. Then devices are switched, are closed down, because that's dangerous for the for the systems, like frequency also means that it determines the spinning frequency of certain devices, and so devices are damaged if we get out of those bounds. And so it's a very small band of different frequencies that are tolerable. This actually is quite a significant reduction in the current energy here. You see we have 395, like almost 400 megawatt extra use of energy to stabilize the frequency in the moment. You have a question?
The energy used to stabilize the frequency, where does it come from?
That will be answered on the next slide. Okay? So this is just this, you can look up, it's the mainsfrequency.com website where you can all the time see the current level of the frequency. And so that's so this is then the answer to the question. To stabilize the frequency, we have a cascaded system. We have primary control. Primary control is directly controlled by frequency, so it's proportional, used in a proportional way. That means the higher the deviation from 50 Hertz is, the more energy has to be used in order to balance it out. The more primary control energy has to be used. It can be activated within 30 seconds and is used for a potential duration of at least 15 minutes. And then you have secondary control, and secondary control takes over from primary control to stabilize the energy. So additional power plant, gas power plant or whatever, and that can last for at least 1 hour, potential duration of at least 1 hour. So it's also triggered by frequency. And then we have the minute reserve, and this is triggered by a phone call of the transmission system operator, noticing that secondary control is not sufficient, there's a longer lasting deviation, and then minute reserve has to come in and take over. So this is gas turbine or pump storage power plants. And finally we have the hour reserve. This takes over from minute reserve. For example, if somewhere the power plant has failed, then it has to be replaced by another power plant which has to be started and so on. And this is actually managed then by the balancing group locally. This is not the task of the transmission system operator. And secondary and minute reserve have to be as large as the largest generation unit of the balancing zone. Why do we have that? This is the n-1 property, which means that even if one of the n elements that I have, which are providing stability for my system, if one of the system fails, the remaining n-1 should still be able to provide stability. And so if one of those systems fails, this has to be it has to be possible to replace that by other systems, that they just increase the power generation slightly, and then they can compensate the loss from the failure of one of those devices. There is actually one, there's also the, like in German it is Momentanreserve, momentary, I think it's the same in English, momentary reserve. That's, I could also say the spinning reserve. The momentary reserve is just, or I know the word in German, Trägheit. It's like if you have a large mass, a spinning mass, a large turbine which is spinning at a certain frequency, then the frequency cannot change that fast, because it takes some time before such a large mass actually allows to reduce the frequency at which it is spinning. And now all those spinning turbines are being reduced in numbers. And so this Trägheit of the system is reduced. That means that if before you had changes in frequency like that, it will be more like this in the future. Much faster, more dynamic changes in frequency, because you will have less of that momentary reserve. And then you need more momentary reserve at other places where you never thought of as being able to provide momentary reserve. And we are actually, in one of our projects in grid control, we are working exactly on that, to provide momentary reserve from power storage, like from supercaps, because they can step in immediately if there is a loss of energy, and then can step in for a short moment, and then other devices can take over. Okay, so this is the momentary reserve that is also there. Now, this one slide I made on the weekend, so that you can see here from the 8th of May, Sunday, we had this, this is also available on the mains frequency website. You can look at it for a 5-minute period. You see the changes in frequency. Just to indicate that here we have something like 49.9 something, and here we have almost 50 or 5. So quite some increase. There was quite a surplus of energy at that day, and just to show you what happened on last Sunday, we had a predicted power generation on that day which looked like this, just for wind and PV. I got that from the transparency platform from that website. And so this was the predicted power generation, and the actual power generation on that day looked completely different, or quite different. Here you had a steep increase in power generation from wind, and then all of a sudden a decrease over there. And the total power generation is not that different. So here it was around 44, 45, here it's only 43 or something like that. But the dynamics were quite significant, and the load at that day was quite low. And so at 11 a.m. it was about minus 100 euro per megawatt, per megawatt hour. And it means that you could really make money by burning energy. Yeah? It was an interesting experience. Sometimes it's interesting to just look it up and see how these prices are developing. So just to see what it looks like today, let's briefly look at the current situation today. Takes a little bit. It's loading. There you see the current situation. Like it's recorded here up to the time 2 p.m. And here you see that we have a little bit of, like here currently, at 2 we had 13 gigawatt from PV cells, we had 15 gigawatt onshore, 1.6 gigawatt offshore power generation, 33 gigawatt from conventional. So it's more than half today from conventional, at least at that time. And the spot price, EPEC spot price, the intraday price was 28 euro, positive. Yeah, you see it's almost the same here. There we had a higher price. At 8 in the morning it was 36 euros. And there certainly the power generation was mainly from conventional. Yeah, it's interesting to see. I think it's interesting to see those developments during the day, how the prices are developing. And we will look at that again in our presentation. So just one brief view on the situation, an interesting situation we had on Sunday. So this is again the balancing power image here, showing again primary control, which has to be at full power, it has to provide full power within at most 30 seconds, and then last for a few seconds or minutes. And then we have the secondary control, which has to step in, and after 15 minutes, about 15 minutes, the minutes reserve will step in, and then this actually can continue. This image is not completely correct. Secondary control and minutes reserve can also extend a bit longer, but after 1 hour, our reserve may take over. And our reserve is something where the balancing group is responsible for, and the primary control, secondary control, and minutes reserve is something the transmission system operator is responsible for. They are working on that. And so this is a cascaded scheme of balancing our power. I told you that just 2 weeks ago we had a visit from somebody from India, and there they only have minute reserve. They don't have primary control and secondary control. And so they have outages because they cannot respond in that way to deviations in power generation. The system just has blackouts. And we don't have those blackouts because we have this system of primary control, secondary control, and then minute reserve. And so in other systems where you don't have that, you may establish power again after a few minutes, after 15 minutes or 30 minutes, but this time in between is not taken care of when you don't have primary control and secondary control. And the ingenious part is that in order to start the primary control, you don't need to communicate. It's just looking at the frequency, which is the same at every location. You measure the frequency locally, and you notice a deviation from 50 Hertz. And if you have a contract for providing primary control, your device has to provide power, primary control power, proportional to the deviation from the frequency, from this 50 Hertz goal of frequency. And so it's a proportional supply of primary control depending on the current frequency. No communication is necessary. Works perfectly. So again, primary control, the facts that I list here are the traditional facts which were valid up to something like 5 years ago. Things have changed dramatically since then because people noticed we need more possibilities to provide primary control power even from smaller power plants. So it used to be that power plants had to be at least like only large power plants could provide that, had to have more than 100 megawatt in power generation. And they were supposed to provide 2% of their capacity as primary control. That means they were supposed to be able to increase or decrease their power generation by 2% within a few seconds. At least 30 seconds provide the complete 2% of the capacity, so at least 2 megawatt within 30 seconds. At least 15 minutes working time. This is used in the UCTE network, but this is the old name, which is now the ENZO-E. Yeah, but it's the same network. UCTE was more the network of the transmission of all the grids. ENZO is the network of the transmission system operators. So it's more the functional network. Secondary control used for smaller imbalances had some minimum requirements. These minimum requirements have been reduced dramatically in recent years. Central control by TSO activated in less than 10 to 40 seconds, also frequency triggered. And then we have the minute reserve, which is triggered by phone calls. Like the transmission system operator calls those who are responsible for activating certain extra devices. And if they don't look at their control panels, and miss those 15 minutes, the system is in problems. And it can work up to several hours, not just one hour, but can work several hours. But the hour reserve can take over after 1 hour, and that is provided by the balancing group. And so this is another market for providing that. The interesting point is that there are markets for primary control, secondary control, minute reserve, and hour reserve. It used to be attractive to provide secondary control power. And in particular, since the capacities that were needed there were reduced quite significantly, the number of providers of secondary control increased quite significantly, and also for minute reserve. And so the price, the markets for that just more or less broke down. Now the prices that you get for secondary control and minute reserve are almost zero. So just a very, very small price for being, it's a price that you get for providing that capacity that in case it is needed, you will step in. And if you step in, you get paid for the energy that you provide. But before, you get paid for the power capacity that you promised. And this price for the promised capacity has dropped down significantly, almost to zero. And so now people try actually to get into the primary control market. And there are industries which try to use like some of their HVAC, like heating, ventilation, air conditioning devices in large factories and so on. They actually can try to use that for primary control, or other large users or large devices which use energy and can provide some flexibility all the time. They try to go to the primary control market because there they can earn much more money for providing that. This is interesting effects of the change in the system. You have a question?
Why is the capacity of the power plant for primary control is much bigger, 100 megawatts?
Sorry?
The capacity for the power plant is greater than 100 megawatts.
For the primary control. That was the old assumption that to provide primary control, you need large power plants which can provide this primary balancing power in a very stable and reliable way. It's just a 2% modification of their power generation, and so this can be done in a very stable way. That was the only reason they wanted to have reliability for providing the primary control power. Just to have a very reliable provisioning of that type of power. And there's no other reason for that. If you have smaller devices, like you have a certain demand for the complete power that you need in order to stabilize the frequency. For Germany, that is in the range of 500 megawatt that you need extra, that you must have under contract in order to provide the needed primary control power. And they didn't want to have too many contractors for that. They didn't want to have too many devices, so they just said we only want the large power plants. They can do that in a very stable way. And now these things have changed, and the requirements are going down for the provisioning of power from like primary control power. Okay, I will show you the new things there. So this is still the old requirements on balancing power. So power plants having at least 200 megawatt, and so at least 2% of the nominal power, or minimum of 2 megawatt. Like what they actually have to offer is 2 megawatt primary control power, either going up or down in their power generation. And for secondary and minute reserve, it was different requirements, like smaller requirements, 30 megawatt, positive and or negative available power, going up or down depending on the frequency. And then the, as I said, minute reserve for relieving secondary control, the minimal potential duration, 15 minutes for primary control, 4 hours for secondary control, minute reserve, and hour reserve as contracted, depends on what kind of contract is done with a provider of hour reserve that is actually traded on the market. And the speed of demand change is linear here. It's proportional supply of power. For secondary control, it's here it says 2% of nominal power per minute, so it can change, but those providers of secondary control and minute reserve cannot respond that dynamically as the others, like as the providers of primary control can do. And so the full power has to be there after 30 seconds, 5 minutes, or 15 minutes. And the response time for primary control is immediate. As soon as you have a deviation in frequency, they have to respond. First of all, like in the beginning, it's only a marginal response. It's proportional to the deviation. But if the deviation gets larger, they must be able to provide the full contracted power 100% within 30 seconds. And for the secondary control minute reserve, the constraints are not as strict. And responsible here is the transmission system operator, and the procurement is done by public invitation for tender. And I have entered a new slide on the current situation on the markets, again for balancing power, primary, secondary, and minute reserve. So the total needed power in Germany for that is, as I said, around 580 megawatt. And like secondary here is much larger, that should be available to take over if something bad happens. And minute also quite a bit of extra power devices that should be there. The ramp-up times are exactly the times that I mentioned on the previous slide, so the time to provide full power. Then there's a call for tenders, for bids on the market. Meanwhile, it is weekly. It used to be, like for primary control, it used to be every 6 months. Now it is a weekly auction for primary control. Also for secondary control, where they have 2 different time zones. And then for minute, it's actually done daily. 4-hour products are sold on the markets for minute reserve. Tender deadlines, Tuesdays at 3 p.m. That's the deadline for providing an offer for primary control. Wednesdays at 3, daily at 10. You can offer minute reserve for this day in 4-hour chunks. You can offer that. And the minimum offer for primary control now is plus minus, like a symmetric offer of 1 megawatt. Increment in 1 megawatt. So you can offer 1 megawatt or 2 megawatt or 3 megawatts, but not 1.5. This is not allowed. And for secondary and minute, it is 5 minutes. 5 megawatt. And increment also 1 megawatt increments. Then you have the auction for all. You have all the offers for providing this power. They are all offering it at different prices. And then you have a merit order of power prices, the allocation. Means that you have all your offers and you just list them in increasing price order. And so these are all your offers, and then you just, like here is your demand that you have, and then all those in the, like up to that point there, they all get, like from the lowest, starting from the lowest price, you allocate them with contracts, and then there's some break point where you have the highest price just to supply the demand that is needed, to satisfy the demand. The activation, like we will come back to merit order when we talk about markets a little bit more. Here merit order is just referring to the sorted order, increasing order of prices of the different offers that were made in this call for tenders. The activation is done like for primary control, unselective. Every device that has a contract is asked proportionally to provide power. You are to the question.
What do the negative values mean?
The negative values mean that power, frequency can go up or down. And if it goes up, then it means you have too much power, then you have to provide negative balancing power. You have to reduce it. If the frequency goes down, you need additional power. So you have positive and negative ways of responding to these changes. So, for example, if there is not too much power in the market, if you have a high frequency, and if you have a large, for example, combined heat and power plant and a hot water storage with a heating device, electric heating device in there, you can switch off your combined heat and power plant and use your heating device to provide the heat, and this is negative control power. Yeah, because you are no longer generating power, but you are consuming power significantly. And this is the type of offering that are made on those markets. Okay, remuneration is for the power price. That is just like they are paid what they had offered. And here for the secondary and minute reserve, it is power and energy price, and the power price, as I said, has been reduced almost to zero. So it's no longer that attractive just to offer to provide secondary reserve power, but you are only really getting money if you actually are asked to provide power. That's the energy price that you get. Okay, so things changed. The minimum requirements on the size have gone down quite significantly. It's only this that you have to be able to offer a specific amount of power, and actually you are checked whether you actually can do that reliably. You have to undergo a certain pre-qualification exam or check, where the TSOs, they check whether you are capable to actually provide reliably those, for example, 1 megawatt up and down. You have to show that you can do that for the specified minimum period, that you can provide full power after 30 seconds, and if you can prove that, then you are pre-qualified and then you can enter that market. Okay. Managing balancing power, how do we do that? This has to be done in a competitive and transparent way. So this is here the pre-qualification procedure to check the reliability. This now is no longer true. Here it says that it has to be advertised for a period of 6 months. That was the case a few years ago. Meanwhile, it is just weekly. And minute reserve is advertised daily for the next day, or also within the day now for the day in 4 hours. So even that is reduced. Reduced to an intraday auction. And the effects of reducing the spinning reserve is that you have a faster change in frequency. The momentary reserve is no longer there as it was before. And so the dynamics of the frequency are much higher than they used to be. So we have, and it means also that it requires faster response of primary control, because primary control is just making sure that the frequency deviation is stopped, that it is returned to 50 hertz, then is guaranteed by secondary control power. Yeah, that is stabilizing actually, but primary control is, the main purpose is to stop this deviation, to reduce it slightly, but they cannot really stabilize it on longer run. Okay, then there are all kinds of new business cases for providing virtual power plants. There you have a group of small power plants, and then you group that into a virtual power plant, and you claim that you can actually provide 5 megawatt or at least 1 megawatt of primary control, for example. But those individuals here can only provide maybe 100 kilowatt or something like that, or 500 or 200. And then you must make sure that you can provide something or some, you can actually offer a certain function or certain balancing control power reliably over a certain period with a certain fraction of that virtual power plant. And so in this way, even those who cannot directly go onto the market, they can do that if they go to an aggregator, and the aggregator then acts as the person who offers the combined capacity as a virtual power plant. And there are lots of virtual power plant providers on the market who combine small devices. You certainly need more than just simple aggregation of the devices, because they have certain uncertainties in the way they are operating, and so you must make sure that you can provide something to the outside world. You can offer a certain profile or flexibility profile that is reliable, even if some of your devices are not reliable. But the combination of unreliable devices may result in a reliable service to the outside world if you just combine them in a reasonable way. So it needs intelligent management beyond simple aggregation. The only problem is you have all kinds of devices at different locations in the network. And now you have the network, and some may be on the same segment of your grid, and others are on completely different parts of your grid. And if all of them, for example, are here on some segment of your grid, you remember this screenshot where we had voltage deviations because there was too much power supply on one segment of the grid. So you may, on the market, claim I can offer that much energy, but on the physical system, you cannot. So you cannot really provide physically the power that you claim to be able to offer on the market. And on the market, the assumption is that we have a copper plate in Germany, in the German system. That means regardless of the location, you can provide the power. And this is a problem. If you have such a virtual power plant, you must make sure that you actually can provide the power, and then you have to look also at the real locations of your devices. And this leads to developments where we look more at local arrangements, and we have to take into account the physical location of the different components of a virtual power plant in order to be able to actually make statements on the capability of a virtual power plant to provide a certain amount of power, of reserve power. There are well-known examples of those virtual power plants. Lichtblick is one of those. They have, I don't know whether all these URLs are working. Forgot to check that. Aha. So it's no longer there. But if you look at Lichtblick, the word Schwarmstrom should be available there. If we go to Vattenfall, I hope that that is available. Like Schwarmstrom is from like Lichtblick has the idea of combining all kinds of combined heat and power plants in the basements of individual houses, and then control them centrally and provide them as extra virtual power plants. And here we have this we don't need. This is from Vattenfall, virtual power plant, also using the individual devices here in houses in order to combine them into one virtual power plant. Just look it up. You can easily get more information here on all kinds of things they do, and Vattenfall is heavily working on services for decentralized energy systems. Others are not doing that much. Yes.
All of these small power plants that form a virtual power plant need to be in the same balancing zone, right? In order to form one virtual power plant.
They should be on the same balancing zone. Yes. Yes. Otherwise, it doesn't make sense. Yeah. So it was simple in the old days where you just had real power plants. That was no problem. Yeah. But now this is definitely, if it is distributed somewhere, it does not make sense to have it in different balancing zones. So I just recommend go to those websites and look it up, what kind of ideas they provide here from the different providers of virtual power plants. Nextkraftwerke, I have to go to that also. Nextkraftwerke is one of the newest providers of virtual power plants, although it takes quite long to get connected here. So they have hundreds of small parts. Here, small parts form the next big thing. So also look it up. They have different concepts on how to provide virtual power, but as I said, the problem is that they were designed initially for the secondary control market or for the minute reserve, and now they all have to go towards the primary control market because the others just are not that attractive anymore. So this is something that is interesting. You see a certain price situation on the on some market. You see a spread in prices. You see, oh, I can make money because I have these spreads in prices. And at the moment where many people go on that or follow that idea, there's so much offered that the spread in prices goes down, and then it's no longer of interest. Yeah, so this is a trade-off. It's some kind of minority game. If you have a few people who respond to that, they can make money. But if it's the majority of people trying to get money from that, there's no longer money available for everybody. Okay, so I don't want to go into more details there. Just look it up yourself and learn about what they think about virtual power plants. So here is one example of the old days, like from 2008. There we had still the high deviations between high prices per kilowatt. Also here we have a deviation, or we have a difference from 50 down to something as zero. So quite some spread in prices for balancing power during the day. And so if you can manage to sell your primary power at those times, or your secondary balancing power at those times, you can make money. Now let's briefly go to the market structures. We'll not get completely through that. I mentioned markets several times already. I'm not the market expert. I just want to briefly show you what the role of the markets is. So we have a large European energy exchange, and there you can trade power, you can trade carbon dioxide certificates. They have gone down in prices also very much. You can trade gas, coal, you can do that for Germany, Austria and Switzerland, and there are many market participants trading there. And you can trade there on 4 levels. So assume you want to provide power for some day in 2 years from now. You have a certain forecast of how much power you need to provide or to satisfy the demand. So you can go on the futures and options market and you just say, I would like to order power for that day 2 years from now, and you have to agree on a certain price. And there are different schemes for that, futures and options. We come to that in a moment. And then there's the day ahead market, where now the day for which you would like to provide power is coming closer and closer, and the day before that you get explicit forecasts of how much power you need during the different hours of the day, and for that you have to buy the power, the needed power, the remaining power that is needed on the day ahead market, which is now called the spot market. And on the intraday market, you are trading within a day for deviations that occur during the day. So you can still trade in 15-minute intervals. You can trade power that has to be used within the next 30 minutes. And these time slots are being reduced in the moment, going down from 15 minutes to 5 minutes. This is currently happening, and people say that it may go down even more. There have been some experiments in Washington, the state of Washington in North America, where they actually had real-time markets available for everybody, and it worked. So then we have the balancing power, which is contracted and then has to be activated on demand. So futures and options. So a future is like a market for futures. That's for long term, for months and years. You buy an obligation, or it's an obligation to buy or sell an asset at a price fixed today at some fixed time in the future. You now agree on a certain price. You say, on the day 2 years from now, I will pay you that much for the power that I ordered today. So this is the future. And then you can also buy an option, and that's the right, not an obligation, but the right to buy or sell a certain asset within a certain time frame, for example 2 years, at a price depending on some reference value fixed today, plus some premium. So you have some premium rate, and you can have some reference value, let's say the oil price, or like Brent oil or something like that. You have a reference value, and you have the right to buy or sell at a price depending on that reference value, and this is fixed today. Like this relationship, plus some premium, and the majority of power trading used to be in this area, long-term trading of power. This is now the importance of that is going down. And then we have the day ahead market, trading for the next day. And on Fridays you trade for Sunday and Monday, not just Saturday but also Sunday and Monday. And here I have now a few slides or few diagrams showing different values. So this is the day ahead prices for the 28th of April of this year. You see here the euro per megawatt hour varying in between here 22, that was the lowest price. There we had 37 and then we have some a medium price here in the middle. So this is showing the price development over one day, for the next day, for the 28th of April. This year is also day ahead market for today. Yeah, for today, the prices looked like this. So the lowest price was something like 12 euro, highest price somewhere over here, 34. And if you compare those two, well, very different. So from day to day, quite some difference. On these diagrams, you also see always the volume that actually is traded for those prices. So for every hour of the day, you have to buy or sell a certain amount of power. And then another diagram showing for a complete month, the day ahead market, the price development. So this is from for 1 week. No, this is for 1 week. So this is that true? This is more than 1 week. This is a month. For 1 month. So there you see the different the price deviation. So sometimes it was rather low. That's the day ahead market. And now the intraday market here for the that's for 2 years ago. Quite some activity here going up, like the intraday market going up to here to like the highest price that was offered was 150 euros. The lowest price was something like minus 50 at some points in time here. And the line here, the lighter yellow line, is the actual price that was paid. And so it's showing the dynamics. Here you see also quite dynamic volumes that were used. That's for 2 days, the 18th and 19th of May 2 years ago. And this is for this year, the development over the last month from the 12th of April to up to yesterday. And you see not very much activity here. We have one peak price there around, that's actually 500. And here you have very low price, although that is the lowest price that was occurring there. But the last price that was paid is not that low. But you see that it's not as dynamic anymore as it used to be. And here is just for the 2 days, the 7th and the 8th of May, as I said here for Sunday, very negative prices. And for the remaining part here, almost zero. So you can't make much money on such a market if you don't get anything for buying or selling something. So this is a problem with these markets, that the prices go down. Okay. And then the question is how long I can tell you something today. So that was just all kinds of diagrams, and one of the important ways the markets operate is the merit order mechanism. I will show you that. I'll tell you more about that next week. So next week we again have 3 hours in a row, and then we have then there is Frohnleichnam, I think, and then the week after that again we have our lectures. Okay, thank you for your attention.